I will start. Sorry, I didn't know, but if you can hear me, let's check with anybody from the teams if he can hear me very well. So
Yes, you're fine.
yes, okay, great. So thank you for this opportunity to talk about machine learning and design optimization. Actually, I'm going to combine both. But today I'm going to talk about optimization, usually how we do optimization in the group. And then tomorrow we will try to say, oh, we can find another way to do this optimization using machine learning. So it's a good story to tell coming from our research group that we work on applied mathematics and fluid mechanics coupled with high performance computing and AI, just to say that we are developing these tools. So today I'm going to talk about topology optimization. What are the numerical tools that will be used to do that? Looking at the sensitivity and design variable. And what is important is to propose for you these general algorithms that you can use later, show you a lot of application to understand the performance and flexibility of this method. I can extend it to thermal problem and even flow distribution if you have time. But tomorrow we will show you how we can stop here, change these approaches, and use machine learning to do the same objective. Okay, so you have I'm coming at the last of the week, so maybe you know about all that. What is the cost function objective function? It quantifies the performance of the system. And imagine this is an energetic system or heat transfer system. You need to set the set of constraints which can describe the dynamic behavior of the system. These are equality constraint, or even more harder, inequality constraint that talk about restriction, don't pass this value, limitation, etc. And finally, you need to talk about the design variable. What are the inputs that affect the evolution of the cost function? So now the question from a mathematical point of view is to combine the three definitions that you have here and say, find the value of the design variable that minimize the cost function while respecting the constraint. And you know that you can find some local minimum in your problem, or if you push forward, maybe you can go and find your global minimum. So, and in the optimization technique, what is difficult? It could be very simple to very complex, and this depends on the physics, depends also on the computational power. So if you talk about parametric optimization, you can see from the initial shape and the final shape, we only change some variable. So we can say that it's similar to the baseline design. You can go further, but keeping the same scenario, but the size and shape change from the final shape to the initial shape. And the most challenging is this one. It's when you change the topology completely, you come from an initial shape and how you obtain a final shape completely different from what you have. And this is where we are going. But bear in mind that it depends on the approach that you are using. You can increase the computational cost, even the complexity of the algorithm. And you're going to ask questions about sensitivity analysis, computational time, as we said, and manufacturability. That means, can we, when we design this piece, can we fabricate it? And its precision. So I'm going to push forward until there so you can see all the details. And if you succeed, you can do optimal fluid flow inside industrial process like you see here. Or if you like aerodynamics, and I'm sure that you like aerodynamics, you can go and improve such process. And what is now, and I can push you to go and seek that, it's everybody is looking for thermal management. And this is very important. You can see the type of pieces that you can obtain in order to have like some thermal management performance inside a heat exchanger, for example. So now, what are the numerical tools that will help you do such an exercise? I'm going to give you all the tools. Some you know of them. Some it's very particular to our approach, but at the same time, you know you will learn something new. So if you want more details, it just came out 2023. There is a paper that talks about all the details. When you have the slide, you can go back and see this paper that show you all the numerical tools that needs to be topology. Let's start now. If we talk about shape, suppose we have a shape inside an initial volume. So I know that this shape, I can, from a learning approach, I can draw it. I can like have an implicit function that represents this shape. We call this function the distance function, level set function. What it's only a function that is positive, let's say inside, negative outside. And if you want to see the interface between the two media, you only look for the value 0 of this function. We call it ISO value 0. Now, if you have this function, you can go and use it to separate a media from one side to another side using, for example, Heaviside function or linear function as you wish, that we're gonna distribute the properties of the density, of the viscosity from your part that you want to design and the surrounding media of your part. Okay. Once you do that, now you are ready to make it evolve in time. And this is where the idea coming. I showed you from the beginning that you have initial shape and this is shape deformed. So something changed. So we know also that the level set function, if you have a circle or whatever distance function you have, you can transport it into your domain or even change its form by casting it into a very simple transport equation. So you have the derivation in time of your function and you convect it, you transport it by a velocity, its gradient. However, it has a small nightmare. It needs to stay a distance function. That means it needs to remain the property of a distance function. The property here could be gradient of alpha equal to 1. So I'm going to insist a little bit on that because this is the main factor of this optimization topology that we are using. So usually what we do, every time we move with this distance function, we stop and then we use a Hamilton-Jacobi equation, which gonna repropagate the levels of this function in order to regain the gradient of this function equal to 1. That means in order to regain its properties as a distance function. However, let's say, okay, this is very good. So now if we go further in time, I mean, if we go to the steady state of this solution, we can retrieve this phenomena, this behavior, this movement of the distance that are not equal to 1, and come back using a specific time step that is different than the time step that you use, and then cast everything into your equation. So now we are getting this equation that is gonna transport the distance or the levels into a distance equal to 1, and you have the function that is convected by itself. So if you combine both, you're gonna have, you move the interface while you are maintaining or pushing that the distance equal to 1. This is a way of doing it. It's very interesting, called the convective level set method, but you can use any other approach. Just remind that this transport equation, if it's a level set, it should have some properties, and this is a way to deal with these properties. Okay, there is a different ways, but you change the transport equation into a transport equation with a velocity, another convective velocity that will propagate the ISO value, and gonna respect a certain condition, which is that the gradient of alpha equal to 1. Okay, if everybody is convinced, so now the information in the design of a piece are not needed everywhere. So there is an idea of having the concentration of all these levels only close to the interface and remove them elsewhere. So what we do is we use a filtering of the function. That means we transform the change of variable. We change alpha into alpha hat in a way that everything, you see, these are all the levels. You can see all the levels of the distance function. We can propagate them into red, blue, and all the levels that I'm talking about are now concentrated into certain thickness, which I call here E. So it's only to help you not deal with all the ISO value everywhere in your domain, only to concentrate your problem if there is no distance function only at the interface. Okay, so in this case, you have the same function, but just you modify the terms. No worry about it. There is all the details taken in the paper. So now if you have a good way of transporting this value, I can show you an example. Okay, I say to a circle, go from here to here. Okay, or to a triangle, go from there to there. I can make sure that I'm not losing the property of a distance function. It stay a circle, it stay a square. Okay, so what is happening here? I have a scalar function alpha. I cast it into this equation, and I said this equation now, the movement It's given, go from here to here, and this is what's happening. I can also, and this is gonna make you now think, I can also propagate different transport equation. I can grow this material. I can have like a function that is designed at the interface of the circle in the normal direction by saying go, 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 and grow. So now you understand, like I can shift material from a region to another region, and I can even increase this volume or even decrease it. So you have all the mechanism now. If you have a shape, to change its form into the desired objective. So now I gave you the mechanism. Now we need to drive it well. We need to drive it in a way to go into your shape that you need, into the cost function that you need. And this is where it needs some precision. And I'm going to just say a few words about we are succeeding it because we are also applying mesh adaptation. Okay, so you can avoid mesh adaptation by having a fine mesh everywhere. But if you have a computational issue problem, you can have the mesh very well refined where you need and coarsen it elsewhere. Okay, and this is a way to do it. I'm going to show you an example. So I don't need a fine mesh far from the interface. All I needed is inside the tube. So my part now, the part that I'm going to fabricate is this part that is inside, like you see here. So it is so nice, I'm zooming in, for the fabrication. Why? Because when you use such a mesh, there is an issue in the form optimization that when you want to go and print it, you will have some defects on the interface. By doing this type of coupling between the level set and the mesh, you can have very smooth interface. So when you print it, you don't need to pass your time, or you can have small defect everywhere on the surface. So this is the two reasons. The first reason is that you can minimize the computational cost and increase the accuracy of your method at the interface. And the second one is related to fabricate itself the piece without having any defect on the interface, on the surface. So this is some defect. This is no defect. You can see if you're going to print this part, you're going to see the defect. Okay, so now I'm combining both. I'm having the interface and I'm having the mesh, and I'm happy that I have an interface that is accurate the whole time. So what makes this drive the interface? It could not be something that I imposed from here to here. It should be the physics itself. That's where our equation comes in hand. That means our equation will be Navier-Stokes equation, okay, where you have a property going through your material. This property should be related to a density and to a viscosity. And if it's surrounded with air, why not? If it's surrounded with water, why not? That's why the level set is going to separate the two media between your piece or your interior of the piece and exterior of the piece. And how we solve Navier-Stokes equation, because it's a two equation, one for the velocity, one for the pressure, you need to have a specific method to solve two equations, two unknowns in this case. Especially in finite element method, you need to respect a certain compatibility of the space. I'm not going to go into the math, but there is a way of doing it by using stabilization method, such as variation multi-scale approach or Galerkin least square approach or other approaches, in a way to have accuracy in the resolution, and also you can bypass this condition that you solve these two unknowns in the same space. Okay. So if you are convinced now, I can solve an unknown velocity. It could be any velocity. So I have an unknown velocity. Now imagine if you have an unknown velocity coming inside your piece, and that's why I can have a very weird shape inside my piece. So, and I can combine it with mesh adaptation to have a very high accuracy, as you are seeing here. So I showed you three numerical tools. The first one is related to the level set to transport the material from one side to another side. The other one is to solve the fluid inside your part, and even if you want, you have something outside your part, but it could be just solid, and you are pushing through inside. And the mesh adaptation that will localize the interface, separate them, increase the accuracy for high gradient, and at the same time having a very smooth part going outside. Do you have any question on this part? Don't hesitate to stop me. If you have a question now, you can try ask it. If not, I will continue. Okay. So let's come to the to our interface and to the shape or topology optimization. So if we have an interface like the old one here, the whole question now, since I know that I can move it from a place to another place, I can deform it. All I need, the whole development that I'm going to show you here will be related and downscaled to this velocity, beta. How to compute this beta on every part, on every point of my interface in order to change the form. So let me imagine I have all the tools, and now all I have to do is to look at the optimization problem itself at the cost function as you see here in order to get this beta. And it seems that people worked on this subject before. So let me tell you first that I have a cost function. It's related to my whole interface of the part that I want. It could be also volumic, but we don't need it in this case. That's gonna give me the integral of the cost function of the surface integral here over the boundary of the fluid. So now the whole objective is how to compute this beta. If you look on the in the community that work on shape optimization and topology optimization, we can write down this beta as a function of some unknowns, as you can see here. U is the velocity that I showed you before. U tilde will tell you what is U tilde, and the viscosity. And this is a very nice way of having this velocity at the interface in related to the gradient of the velocity and into the normal. So remember the circle that went in this direction? Okay, it could go in this direction or in the opposite direction. Okay, and it follows the variation of the velocity. So what is in this case the U tilde? It was we call the adjoint velocity. And this comes from another equation that you need to solve, and I will tell you why you need to solve it. So finally, if you look at all the equations that I showed until now, you have the Navier-Stokes equation, okay, which is similar to the adjoint one. You have the adjoint one that can also have a transport of the gradient of U tilde, and you have another convection term here. You have the stress term for the pressure and the velocity, and also the incompressibility in this case of the adjoint velocity function. So from where we derive this one, okay? So if we go back also to your first course, I remember that you look at the Lagrangian, okay, that gonna cast all your Lagrange multiplier for the cost function, okay, and the variation of your physics. So we can count here the U tilde is coming as a Lagrange multiplier for your Navier-Stokes equation, P tilde for the divergence of U, and you have your first cost function that I showed. So now we need to derive this Lagrangian in respect to all these variables that I'm showing in order to make sure that its derivative will be 0. That means we are going to seek a minimum. And by doing so, we can also verify our equation, derive our adjoint equation, and also handle the unknown at the interface that you're looking for, beta. So first, if you derive your variation with respect to the adjoint variable, what you will see here, you will see that you have the divergence of U, and you have the Navier-Stokes part equation, and this is true equal to 0 because you are solving it, and I hope you are solving it well, in order to push it to 0. So this term, by fabrication, will push itself to 0. So we are happy with it. The second one, it's up to you to push it to 0. It's when you derive in respect to U and P, of course, after all the mathematical integration by part, analyzation, I'm simplifying it, you end up with all these 4 terms. And if you look at all these terms, we're gonna see why we need that divergence of u tilde equal to 0 with this part of the equation equal to 0, which are what I showed you, the adjoint equation. So now we are solving Navier-Stokes equation that verify u and p. We derive another set of equations which are the adjoint velocity and pressure velocity to solve, and this comes from here, and with additional terms that are related to the boundary condition, which gonna be related later also to the cost function that you're gonna impose. It depends on your problem. Okay. So if I move forward now and I look at the last part, now I need to go back to my interface, okay, which is the velocity beta, and there is a way to relate it by using the deformation of the velocity, as you see here, and it's related to with a simple Taylor development. We can see that it's related to beta, a constant given constant velocity, and the divergence of u to n. And if we do again this derivation now of the Lagrangian, okay, in respect to what we saw before, where all the terms are going to 0 and we still have these terms to finalize, we end up with a beta multiplying a function which is now the derivative of the Lagrangian. And one way to make it to make the gradient go linearly to 0 is to set beta equal to minus u divergence of u tilde in respect to n, and the gradient of u in respect to n, the gradient of u tilde in respect to n. So by doing that, I expressed why beta is related to this term, and this beta now is gonna be used at the interface to integrating itself with the cost function, verifying the Navier-Stokes equation because you have u, verifying the adjoint equation because you have u tilde and p tilde, and now pushing your distance or your form to the form. So some information related to the volume of your piece. We are saying here to avoid the case where the solid domain is closing the entire design domain, so you don't have a space. So this is can come in pressure drop minimization. Or imagine if you have a drag minimization and you don't control the volume, what will happen? You will erase your volume, you will erase the material. There is no, the material will like go and shrink and go out. So we can add a checkpoint that gonna check on your volume of your material that you are driving from one iteration to another iteration. And it's very simple to compute, but it's related to the heavy side of the level set. So all the framework now is connected. You can compute it by that way. And finally, you can apply a volume constraint by if then else simple algorithm. But remember that you are going to start from a initial volume, maybe randomly generated, and you have a target of a surface, let's say, of a volume of the material, and you're gonna gradually decrease toward this volume. This is a good way to help you cannot jump from one form to a completely different form. And the idea is to go iteration by iteration towards your objective form. And this is really related to the way we choose to solve this problem. So let's see now. I told you a lot of information how should this numerical method now be coupled to build a topological pressure framework. I talked about primary Navier-Stokes. I talked about adjoint Navier-Stokes. I talked about the level set advection, how to compute the sensitivity, and mesh adaptation, and geometric constraint. So the idea is can we have a solver that output and serve as an input for another solver? So I mean you compute the velocity and the pressure, and you're gonna be needed this information into the adjoint equation. And when you finish the adjoint equation, you're gonna construct your velocity at the interface. So everything is related. So that means you're gonna have to solve this equation one after another. Okay, and we're gonna use the adjoint and the Navier-Stokes in order to derive the the velocity convection at the interface. And also, this is the plus that we have. It's like mesh adaptation can help you increase precision and reduce computation cost. So if you want to see it as a general algorithm, if you want to implement it, you can say what I have now in Python or any code, and what do I don't have, so I construct the rest. So you have an initial shape, okay, and if you can solve the Navier-Stokes equation for the flow that goes inside this shape, any shape, it could be a big block, okay, you have now the velocity and the pressure. So you're going to use this velocity and pressure to cast them into the adjoint equation. You can see here the velocity coming to help solving the adjoint velocity and the pressure velocity. Once you have these two unknowns or four unknowns, but you need the velocity and the velocity adjoint velocity, you can construct the your sensitivity or your parameters that you modify every time, and by miracle you can use the level set or the transport of your interface by casting by using this beta as a convective function in your level set. Now you had a mesh at this point. You now convect your interface to this point. So that means we reuse the mesh that we have here. The interface moved. We remesh at this point, and then we do the checking if we are converging or no, depending on the volume or surface constraint. And then we iterate for another mesh, and then we iterate. If we have the final shape that our objective function is respected, we stop, and we obtain a final shape. So this is basically the global algorithm. There is a lot of details in order to obtain it, but it becomes now a general framework if somebody has type of these tools or he need to complete them. If you have a primer Navier-Stokes, you can have simply the adjoint solver. And to code a level set function is very easy. It's just a transport equation. Maybe the mesh is critical because you don't have precision, but not everybody necessarily need this mesh. If you have a very fine mesh, you can go bypass it, and then you can iterate in order to obtain your final shape. So this is a numerical example. We are saying in this example, it's very known, very, very well known. It's called the bend pipe. I don't know if you see it during this week. And the idea is to we have a flow going from this side, going down to this part here. And the idea is to optimize the shape of this channel in order to have, respecting this cost function, which is saying indirectly, I want to have a delta P, control this delta P and have minimum effort to go from this side to the other side. Okay, so this, remember that this cost function will help you when you derive it. Will help you design all the boundary conditions that you need for both the adjoint and for Navier-Stokes equation. And we can put a surface of reference. That means the surface is going to obtain here. I don't want it to exceed 25% of the whole surface. Okay. Okay, real number here is 1. That's why we are using non-dependent equation, so they can converge. So that's why, because the real number is low. So in this case, as I told you, you can use the cost function to derive it and recompute the boundary conditions that you need for the velocity and for the stress on the adjoint equation. And the objective is to draw the optimal path that connects the inlet to the outlet and reduce the dissipation power or the pressure dissipation. So we can have a pressure drop that can be regular or singular, and look at the test case. This is my initial shape. I'm helping it just to not to miss a region, but we can change this. This is randomly designed, and then it will start iterating. So at this point, just remember that no miracle is happening, only a level set function being derived from a region to another region using this beta that is in function of all the whole system. And if you continue to iterate, you continue to iterate. having in mind the constraint of the surface, you are going to end up with this final form. I'm going to pause to it. Okay. So your flow is passing through this channel, and all the other parts, you don't need them. You can even extract this part and print it. Okay. So this is the initial mesh, and this is the final mesh. You remember when I say mesh 1, mesh 2, mesh 3, and you can iterate. So you can start from this mesh, any randomly mesh. You can see that there is a region that is not used anymore. It's only a square. And finally, this is your part. So this is what is happening in your computation. You can look at every point or every region, how the cost function is decreasing in order to have a conversion of the cost function. And this is where you can stop. You can do like a stopping criteria, or you can fix a number of iteration as you wish. Okay, so let's see if it works in 3D. There is no difficulty at all to go into 3D. You have one inlet from one side, we have another inlet from side. You can create mix material between the two domains, and then you can look at it, how it's gonna drive the level set into the region, into the needed region. Okay, and this is really interesting to look at the final shape, because you can appreciate the mesh importance in this case. But again, it's not mandatory. It's just for higher precision. Now, this is a very interesting test case where we have two inlet, two outlet, and remember that you can change the boundary condition in order to respect a certain design or no, by meaning that we call it the dual pipe. You can put a criteria that means what is going from here inside should go from the outside, or you can let the outside, the outlet free, so the flows that going into your part can exit from up or down or whatever. So this is a very interesting, and here we augmented a little bit the percentage of the volume of the surface of your part. So it's similar to the previous test case. You can see that now the flow go past this blue zone, and since we are imposing that both outlets should work, so it's going to distribute the flow from on the first outlet on the second outlet. Okay, and this is all the details about how it gets there. Now, if I let the one of the outlet free, and there is no condition on it, the free is free, no constraint on the outlet, so I can choose one of up or down. This is a random choice, and then say why I need to go there. I can go from inside the one outlet, but I will increase a little bit my volume, so all the information will pass with minimum effort on the pressure. So if you can compare them, this is a real comparison with other people doing the same thing but different approaches. We can see that it's the constraint outlet, how it looks like, and the free outlet how it looks like. Okay. Now if you go to 3D but you increase your complexity by having one inlet and outlet, because we are inspired by different outlet, and you can see that you can have a certain form that is minimizing all the displacement to go and seek the outside, respecting the volume constraint. And we tried another example, which is symmetrical, and we find out something new in this case, that you can say yes, it is symmetric. Why simulating the 3-dimensional? We can have like a square, we can cut a part, or we can do like a symmetric boundary condition and take only quarter of this cube. Yes, if you want to do this part, but if you continue pushing it, because this is a local minimum, maybe if you continue pushing to see if you can get something better, look what happened. This is only for confirmation and for validation with other approaches. And if we continue, we left it iterating, and this is what we get. So it's detached, and it forms a better communication between the inlet and the outlet without having this maybe lose of time or lose of decision between the communicating channels. And this is what we get, where we improved even the form by more than 20%. Okay, another example here where it's taken from this paper, where I call it the dancing man, because it has a head and arm and legs. So you can see that you can design different shape. Imagine if you multiplicate that in like different in a big car piece, you can really obtain something nice. But we are creating benchmarks here that are integrated into the papers that you can see later. So if I go now, because I'm looking to the time, to the thermal coupling, okay? What happens if I gonna add the thermal? You should understand that the thermal, it will only add equation, and you need to do this derivation again in order to get in the same algorithm what are the relation with the temperature and what will be the cost function related to the temperature. And so if you go back to your classical resolution of equation, we will solve a convection diffusion equation. Here it's related to temperature, so I need to put the parameters of the temperature, which are density, capacity, and conductivity. And then we solve it again by finite element. Here there is no big issue to respect a compatibility between the spaces. We put FMS, but it's only a simple stabilization approach to solve this type of equation. So why we need it? Because if the convection dominant is important, or you have high gradient temperature, it helps in a finite element approach. So I have now added another equation to my system. So remember that I have U and P. Now I have U and P and T. Okay. So remember, if you want to distribute the parameters from one side to another side, in the case of only flow, we had density and viscosity. But if we have now the thermal resolution, we need also to mix the property for the density and capacity and conductivity. Pay attention on the conductivity in order to respect the flux from one region to another region in a linear approach. It's very good to mix it or to combine it in a harmonic or geometrical way, like I'm showing here. Okay, so now we have added to our equation, the first two equations. We have added a convection diffusion equation for the temperature. So we have three unknowns, U, P, and T. The U that you have here gonna be used to transport your temperature. So again, your adjoint system will also, if you derive the same way that I showed before, will inherit again the temperature adjoint, and you need to now solve this system in order to push the derivative of the Lagrange into zero. So that means you need to solve your first set of equation, the second set of equation, and also now how all that will contribute again to push my interface through a convective velocity that handles or take into account the velocity that I showed before, the adjoint velocity, and the temperature. So this is where it is. If you follow the same strategy of developing, you will end up with another beta, which is related to the same part as before, plus a term related to the gradient of the temperature, which is logic. And if one is multiplied by the viscosity, the other will multiply by the conductivity. So this is what you get. So now I have again my whole system. By adding the temperature to it, I solve three equations, three adjoint equations. Maybe for you it's too much, and then I get a convective velocity. I use it to convect the interface, what we call the level set, if the interface move from one location to another, maybe I can follow it with a mesh adaptation, and then evaluate my cost function. If it's not respected, evaluate also the surface constraint if I have the volume constraint, and then iterate in order to converge my system. So there is also particular attention to boundary condition, but since it's a scalar, maybe it's not that important. So I have dropped here all the type of boundary conditions that you can imagine on the inlet of the outlet of your part, where it comes, and on the rest of the domain, which I call it wall or walls, for everybody, for U, P, T, U tilde, P tilde, T tilde. And then now I'm ready to look at my objective function. What do I need? I need to move it in respect to a minimization of the pressure drop, or I want to use it for a maximization of a heat transfer, or both. So I can combine. I can combine, as I showed you before. The same example was related to this part of the cost function, which was related to minimization of the pressure drop from one part to another, from one inlet to another outlet. And I'm also interested now in transfer. What I want to do is to maximize the exchange of temperature. I want that the exchange of temperature will be maximized. But what does that mean, omega in this case? We can call it weight. I can have 50% here of this information against 50%. So there is a weight into the multi-objective function. So you can put some weight, you can adapt the weight, you can evaluate the weight. It depends on the test case that you have. But remember, if you have two objectives to attain, you can have this condition. If your hydraulic can go up, thermal can go up, or hydraulic can go down, thermal can go down. So you need to it depends. It really related to the problem. So now let's have again our general algorithm. Okay. It's like a question. What should I now solve? What should I remember to solve? So I can solve. Remember, I can solve one to feed the other. So yes, Navier-Stokes, when it's solved, it gives you the velocity. The velocity will be used to convect the thermal equation. Now I have UPT. UPT will be used in the adjoint thermal equation, and then it will be used into adjoint Navier-Stokes equation. So you can see that everybody is feeding everybody in order to complete the system. Okay. We can put it in a general algorithm so you can remember what you have implemented already, what you need to implement it, and this is the additional terms in blue that are related to the temperature part. So if somebody has already developed a Navier-Stokes part equation, like a simple steady equation of Navier-Stokes, it's very easy to add the convection diffusion equation for the temperature, and very easy to come and add a source term here. It's completely independent on the unknowns. This term is seen as a source term for the U tilde, P tilde. You can also design from the same equation. If you have the convection diffusion equation of the temperature, you can have also the convection diffusion of the tilde. It's only a change of variable and change of sign in the convection. And then from all these unknowns that you get, you can construct your control velocity in function of U tilde, U, the temperature and the temperature tilde. And then this beta will be used to convect your interface. And then you know the story, and you can iterate until you get the final shape. I'm not going into a lot of detail. I set only one example in this case. It's a 3D heated tube that has this characteristic. So you have an inlet here, an outlet from the other side, and you have a heated region on the middle. This is a well-known also example to see if, because I want to augment or to increase the increase the temperature exchange. So this region, it will be interested to be seen by the system in order to try to make use of it the maximum possible, but at the same time go directly to the exit. Okay, and we'll see what will happen. So this is what will happen. you can see that I'm trying to minimize maximum possible, benefit from this region, go back and exit. So it's really, really interesting from a geometrical perspective. This is all the details, the fingering that you can see here. And it looks a little bit, not that like this, the industrial part that I showed at the beginning for the car or for an engine. So I know it's simple, it's simple rectangle, but the form that we are getting is really nice, and you can look at the details in meshing in order to appreciate the accuracy on the interface. Okay. So we went into another test case, but to see if it's reacted, if it's responsive to this type of plate, additional plate for the heat transfer, for the heat transfer. And you can see here, it's like it's benefit from the first one, it's benefit from the second one, and it goes out. Okay. Okay. I have a last part, very small one, but this is gonna help me introduce the second part for tomorrow that related to machine learning. Okay, you can say, I agree with you that it's too much. Okay, can we simplify all that? This is the teasing for tomorrow. We need to solve Navier-Stokes. We need to solve three equations, additional three equations. Imagine if you have that in time-dependent system. In maybe with turbulence. And then we're gonna just convect a little bit the interface and then check if it's good, if not good, repeat the whole six equation. So maybe we are developing that and we are happy with it, but also we can, in some application, find another way to bypass everything and to solve and to replace this mechanism of looking for the best form by a learning mechanism, by deep learning mechanism. Can a model learn how to get to my final shape if I tell it, this is good, continue, or this is not good? So this is the introduction for tomorrow. And we did it on flow past object in order to create like a NACA profile, as you may see in this week. But before that, I did it also using this approach just to show you that it could be doable. What you need here is the cost function. You need to decrease the drag function. Okay. The surface of constraint is very important because you can lose your material. Okay. And we tested for different real number. Okay. So the flow comes from this side, goes out from here, and we can have slip boundary condition on the wall, whatever. So the question here, the importance of the surface constant, as I told you, and how can we have a optimal shape? We start by a cylinder, and when we increase the Reynolds number, you will see some nice shapes that looks like the NACA. So we are saying that nature is good. So for Reynolds equal to 1, this is what you get, like oval shape, okay, which is not maybe UFO, but it's like not very well aerodynamic, because for Reynolds 1 it's very difficult also to erase all the drag or remove the drag. It's like the flow is already very laminar. So yes, we checked some people that talked about that, even for smaller Reynolds number 0.1, and it looks like it's going into the good direction. Okay, and we want to Reynolds equal to 1, and then Reynolds equal to 10, and then Reynolds equal to 20. So you see that there is not that much change into shape, because it's not very well responsive from Reynolds to 10 to 20. We are not changing that much the physics. Something will happen when you start increasing the Reynolds number. Okay, and we were worried at the beginning for this point that you can see on both sides, and this is not easy to get rid with them because we are not controlling we are not controlling the region by something else. It's only a material driven by a convective velocity. Okay, remember tomorrow we'll tell you that we can control that by nerves, but here the shape is free. So there is a challenge that when something happened, it need to curve again this front position. So we went into Reno 2000, 200, and then when the flow changed its shape 500, we start seeing something nice that looked like a NACA. And even for 1000, we can see more round on the front, and for 2000 even more round and symmetric. So this is minimum drag and this is why it's symmetric, and it's used by this approach, which not necessarily, and I will ask you the question for you, not necessarily the right method, especially if you go to Reno 5000. And if somebody can tell me this, he can really win. Why we cannot go even to 5000? The whole system is functioning. All the equation I can solve them. But if you go to 5000, there is something happening, and it's not well adapted what I'm proposing here. Can somebody comment on that? Okay, if not, it's really related to the type of resolution of equation that we're solving, and since they are steady in nature, I'm not accounting that much for the evolution and everything, so I'm not very comfortable by solving something very turbulent without taking into account the time dependency. Even if we have a turbulence modeling, okay, that gonna converge to maybe to a steady state, but you need to solve them not only one time like I'm doing here. You need to solve them until they converge. So you imagine now the amount of computation that we will have to do. So for every iteration, for every movement, you need to converge the whole system in time. Now it converged. Now I can loop and go back. It can do both because it's if it's automatic and everything is well programmed, you can click the button on Monday, come back maybe on Sunday, and you have your shape. This is a good way. And there is another way that we're going to propose tomorrow. It's the coupling with the machine learning that make you indirectly independent of the physics you are solved, because it's a mechanism that learn what you want and try to go into your objective. And now with the perspective, what are challenging? The challenging is when you have two-phase flows, when you don't have only one material, when you want to mix properties, that means the media that you are sending is not only one flow. This is a very big challenge now. They are working on it. It's related to the multi-phase flows that we can have, and it's related also to flow distribution that we can say. And I'm going to show you one example maybe on that, where the cost function going to be more complex than you saw before. So this is our system. We have a flow coming from inside, and then it's gonna get out by all these small tubes. Okay, you can imagine it at a big scale as a distribution of the air in my office and to the building. You are pumping the air, and you want that everybody has the same amount or has the same flux, same flow going out from this tube. So it's really challenging because the inlet is in the center. So if you want to go and distribute this, is not that easy. So we went into creating some material in order to drive it left, right, up, down as he wants. And then we looked at the distribution that we get. and we were really happy about it because it's nice and symmetric. Okay, and it represents a good perspective for the future. So now we're gonna inject inside this tube not only one fluid flow, we're gonna have an inlet of the air and maybe another inlet of something else, particles, and we will see how the distribution will occur. So finally, I hope that well, I said it's a small quiz. I can send you that later. So if you have any questions, so it's nice now to exchange. If I kept some small time for that. Stephanie, can you hear me from there? I'm worried that there is no comment. Maybe nobody is hearing me for 1 hour now, 1 hour and a half.
We can hear you. Sure. We can hear you.
Okay, but the quality of the sound is really not good. So I think only people connecting at Teams can really ask questions or discuss. Do you have any comment or discussion, or are you familiar with all these type of equation? Is such framework difficult for you to implement? If you can ask a question, for example, what is the most difficult thing to implement based on all this equation? I'm going to show them back all the system. Okay. Just to a small reminder, this red zone could be replaced by density distribution, by volume or volume of fluid method, by a tracking interface, by ghost fluid method, but anything. It's just the idea of having an interface that could be tracked or could be convected or could be transported. Okay, it will be related to a certain velocity that you're going to compute. And this velocity is related to all your physics that you are solving and the constraints that you are putting to your system. So we did it only in our case because we have already this type of equation, but no need to stick to it. You can change it. Actually, the comparison that I showed before on this one, there was using no mesh adaptation, and here. And they were not using a level set function. They were using a density distribution.
I have a question.
Yeah.
Yes. Thank you. Great talk. What I understand from your talk is that there is no really an implementation from your side that we can download and use it. Because I'm an engineer, I'm not much interested in derivating equation, now much in implement it.
Yeah. It is a very good question. I'm gonna turn the question to you. It's not that there is no K epsilon model, or there is no, I mean, the system of equation that I proposed here, it's now findable anywhere. If somebody wants to use it, he can contact us, and because we are having our own library, it is C++ finite element library. But if you take it from a perspective of having an open form or having a Python or any library, if you look at these type of equation to reconstruct this framework, okay, is not that complicated because it doesn't require a lot of implementation. Now, if the physics are more complex, imagine the density that you see here, okay, it's related to 2 fluid flows. This is very challenging, and even new PhDs will be open in this direction. Imagine now you have the time dependency and nonlinear terms for the convection you need for Reynolds 10,000 or Reynolds 10 to the power 5. So you need to add even more additional equation here that are related to convection diffusion reaction equation, like such as K epsilon or K omega or Sparrat Armaras if you are doing aerodynamic. But to design small like heat exchanger, to design this type of approaches, it's really easy to put in place. Now, for tomorrow, we will suppose that you have a solver. We will give you the machine learning tools. okay, which are related to a new branch of machine learning. Okay, and in this case, you can download them because when we created them and when we updated them, we also took them from PyTorch or any library, and we adapted them. So in this case, we're going to share with you all this material. And if somebody needs information on this, remember that this is a paper that gives you all the details. To solve this equation are not complex. Now everybody can have them, but if somebody is doing it for its own internship or work or whatever, we can help. We can definitely help. For free because you are participating to this course. This is good, Stephanie. This is good way to say it, Stephanie. I cannot hear. Hey, Patel, you have another question?
I have one question. Can you hear me?
Yes.
Yeah, so I was thinking that instead of level set, if you change it to another kind of tracking methods like phase field methods, would the approach works well? Very
good question. We are developing the phase field in another topic, like for boiling and for changing of phase changing. But we didn't couple it with here. Yes, you just say very good remarks. It could maybe give something more interested, especially if you have phase change or if you have different multi-flow fluid. So Patel is saying that this part of the level set could be replaced by a phase field resolution. The phase field resolution look a lot like the level set, but it has incorporated more physics, and I like it very much, especially when you want to compute a surface tension. It's only derivative of the primary variables rather than constructing the curvature and doing a lot of stuff. So I agree with you, and it could be nice, but we didn't try it yet. We finished this framework recently, and that's why we published a few months ago. Very good, very good.
May I ask another question also, Professor Hashim?
Yes, of course.
Yeah, it's actually coming from one of the audience in Udine from Vanessa Kuhl. She asks, is it possible to on whole creation in the frameworks? For example, can the topology change, or what happens if you start without holes in your initial design?
This is a killing question, very important question. That means you're gonna germ material. We are developing it now. I didn't show it because we didn't finish it, but we are creating material. That means there is a zone, there is no material, and then start creating. A few people don't do that, but it's very important because, as you said, we prepare the domain in this direction, so it drives itself. But if you want to have something completely new, okay, and sometimes not necessarily in the region that you are putting, you need to have a growth of and germ of material, and this is what we are implementing. And if you can do that, you will be very good in answering industrial looking for such a part. I will show you this part. This one here needs what you are saying. This type of part, okay, it will need, because it's really filling all the domain, and you need to, especially if you have a boundary condition like a fluxes or somewhere on the cold plate, we call it cold plate, and it's very important that you have a mechanism that can create and erase material wherever he wants. And we are developing that now.
Thank you so much. And would you be able to make the presentation available also on the website? Okay.
This is all. I have more slides. I didn't show them because I wanted to keep some discussions. I will share everything with you.
Okay. Thank you so much.
Yes. Tomorrow I will do a small introduction and teasing for you all. Why he's killing himself? He's like replacing all this physics, all this equation now with machine learning. It's not that I'm going to push that. There is application where you need something like that, and there is application where you don't need a lot that you can do it differently. And this is the good of this, the topics of this course, scientific machine learning in design optimization. You need to understand the design optimization, how can be occurred, what are the equations that you use. Sometimes it's very complex for a little bit of result. Or can machine learning now replace that and go beyond? The answer maybe is yes, and I will show you tomorrow.
Thank you.
Okay. I hope you enjoyed this course. I'm pity not with you because something personal happened in my side. Good thing. And I hope I can meet you or see you in another occasion. I will see you definitely tomorrow at the beginning, and then my colleague will push you on showing you all the details about the machine learning part. And on this part, you will have access to Git to download and to play with it.
Thank you. I think it concludes.
Okay.
So I'm talking on behalf of, but they are not responding.
Okay. See you all.
Thank you.
Stephanie, I will call you. Bye-bye.